north pier and north abutment. So this is when the triaxle truck, so a 72 cube truck goes over the bridge, and then with the initial model, we had some distance to the measured data out here, and there were several layers of global model updating, including updating concrete properties that we got closer, and then added safety curves that were made out of concrete, and they added significant stiffness, and we got closer. And then we looked at the negative moment areas over the piers and concluded that we needed to reduce the stiffnesses by about 10% in those areas due to cracking in the concrete deck in the negative moment area. And we got very close to it, but to start with, we also had a good model. This is another strain gauge that is near the north pier at the bottom flange, and you see the strains are in reverse order. And strains were about, in the positive region, about 100 microstrain, and in the negative region, about 50 microstrain. I also should say that we had very clean data working with good sensors and good data acquisition boxes from Geocom. Then using the updated model, we did 3 types of load rating, and it was with what is used in design offices with Vertus, and then we also used the NDT data, strain gauge data, to update the model, to use that for load rating, and then you use the updated finite element model also for load rating. And 2 things, and then we did it for inventory loading, that's like day-to-day loading, and operating loading, that is for extreme loads and permit loads. 2 things to mention here, you see that these girders 1 through 6 do not show symmetrical capacities, and this is due to the fact that there is a large sidewalk on the right side when you're facing north. So you get a higher capacity, especially when you model that. Also, overall, near the edges, you see similar capacities, but in the middle, you see that we have additional capacity in load rating. And the question for designers is that, what do you do with this additional capacity? Do you try to design slimmer bridges, or use this additional capacity for to compensate damage in the long term? Dr. Bell is going to speak about that. The second model is the enhanced designer model that has smaller degrees of freedom, much easier to build, and we take advantage of frame elements to model girders, although these are in computer graphics extruded to show a steel girder, but these are one-dimensional beams, and the deck is modeled with shell elements. So we have about 1/10 of the number of elements and degrees of freedom, perhaps less. Now, again with this, here we looked at 2 strain gauges on girder 2. It's an interior girder that we saw smaller differences. And here it shows the measured data, original data is in red, and updated data is in blue, and we got closer to the model. And this data was used again for load rating. This time we used LRFR to look at ultimate capacity. And again, we see similar ratings at exterior girders. Interior girders gain extra capacity. And in terms of system behavior, we see stiffer exterior girders that has the concrete portions of the parapets on the top of the concrete deck, and basically increases superior in terms of load rating. Something about instrumentation. I very much enjoy working with strain gauges and tilt meters and accelerometers because they're reference independent. In the lab, you can use LVDTs or RVDTs for displacement measurements, but they need a reference point, and it is very difficult to do it even for a small bridge like that. And we need to have high resolution measurements. Another, then we used cameras for use the digital image correlation data. That is, cameras take images of pixels that are marked on the girders, and they also verify these measurements with LVDTs, and they came very close. So in terms of model calibration, here we are looking at the stop location data. Before we were looking at crawl speed data in the previous model. And here we see that the original and updated model, black, went to red and got much closer to the stop location data, and this is a truck stopping at about 10 points on the bridge. And again, at another location, we see similar results, and especially when displacements are larger, you see that we get much closer, and the range of displacements are about like minus 0.04 to plus 0.04, so less than 0.1 inch measurement. So we get very accurate displacement measurements. Ongoing research is that we also recently did a second test with dynamic testing, used an ATS dynamic shaker with 9 high precision accelerometers and 9 locations of excitations. 9 times 9 gives us 81 transfer functions in frequency domain, and we are using, JC is using that data for model calibration. So we are going to have both static and dynamic model calibrations. A quick comparison between the models, because anytime you have you're making models, the question is that you want a fine model, coarse model, medium model, and a quick comparison based on our experiences is that there's how much time and money you have to spend on it. Obviously, with student time, they have infinite number of hours, right? So with the researcher model that is more detailed with solid elements and shell elements, we had direct access to element stresses and strain calculations, detailed behavior, and obtained stresses directly from real 3D system behavior. So we didn't have to make any assumptions that what part of the deck was fully participating in this composite action between the steel girder and the deck. Where in brim model, we use beam assumptions, then we have to calculate the stresses and strains based on the section of the girder and the deck, and need to define effective width. Detailed model is more complex versus brim is easier to use and easier to make changes. So in the interest of time, I quickly say that we were able to update two 3D finite elements with similar results, use them for load rating, use digital image correlation for independent displacement measurements, calibrated the models. There are pluses and minuses in using different types of models, and the updated models can be used for load rating and bridge management.
Our actual realist on this project is Brian Brenner of FST, so I'm him right now. How this project started was Whatever Happened to Long-Term Bridge Design was an article written in 1990, and the idea was that there was more redundancy